Great. Yeah. So let me go through, I think kind of a relatively newer technology. We're looking at incorporating light with AFM, allowing us to do IR spectroscopy, basically. And so let's kind of get a lay of the land on how the kind of current commonly used analytical techniques that we're all familiar with, we are effectively trying to understand if we're using optical light or if we're using electrons to probe our samples to really understand them. Are we looking for elemental information, things that we would get with our TEMs, our SEMs, or are we trying to look for molecular information, things that more commonly we would be doing, XPS, TOF Sims, Raman to do. Analytical chemists, they really like to get into that FTIR space. But fundamentally, where we're stuck is resolution, right? So we end up in a location where we'd really prefer to get molecular information because we will be limited with just elemental information, being that, fundamentally there, we're just, looking at what atoms are building up in materials. But with molecular information, we can do a lot better job kind of identifying what materials are physically there in terms of the molecular species, not just a collection of carbon, oxygen and such. But like I said, you're kind of stuck in this realm where you're not getting great resolution in that space. And so if we can combine this with the high resolution capabilities of SPM, then we can kind of bridge that gap. And that's really what I want to present to you today, is how we do that with our technology. So fundamental idea, FTIR, we're stuck with a large spot size. We are trying to focus, light in the IR, which is in the microns of wavelength. Oh, pardon me. And, even if we could do the best diffraction limited spot, we're talking about, lambda over 2. And so there, you still might be talking about 2 micron kind of resolutions. We'd really like to see if we can get that down to tens of nanometers or even less, even sub 10 nanometers. And we are able to do that with introducing that AFM probe. So this kind of gives you a cartoon of how this game is going to work. We're going to have a laser excitation source, and that source can be really quite broadband. You're not limited just to the IR space. You can work in the UV all the way out, potentially to the terahertz space. Now we haven't shown the terahertz working in this technique yet, but other groups have kind of dabbled with that, and so there's definitely the potential for this. But definitely this UV to mid IR space is really no problem for us. We take this light, we focus it with an off-axis parabolic mirror, and we project that onto the end of the cantilever. And the idea there is that you're going to generate a local hotspot with the end of your SPM probe, and that's going to effectively reduce the imaging area. But to go a step farther, what we're going to do with this photo-induced force is we're not going to measure photon scattering off of the end of the tip, which would be commonly done with, let's say, a TERS technique or a tip-enhanced fluorescence technique. We're actually going to feel a force imparted on the tip by the absorption event in the sample. And what this is going to provide for us is a very localized measurement. So only the force is felt underneath the tip. So just think of your van der Waals forces that you feel under the tip, but now you're feeling an absorption force that is being generated by the sample. So now we'll just be limited effectively to the spatial resolution of the end of the tip. So here's kind of concept of how that's going to play out. We're going to use kind of a multimodal technique. So a bimodal technique, based on kind of some of the previous talks, if you think about KPFM, EFM, those types of traditional scan probe techniques, but think of doing them in a bimodal mode, not a lift mode technique, but an AC bimodal mode. Then what we're going to use is 2 mechanical modes of the cantilever. Your fundamental mode, we'll call it F1. Your second mechanical mode, we'll call it F2. And the idea in the way we employ this is we'll use that second mechanical mode to take topographic measurement, which you'll be commonly used to. One of the reasons we like to do that is, one, we get the cantilever very close to the sample, which gives us more force measurement in the absorption, of the laser and the sample. And secondly, we get to use a cantilever and kind of trick it into acting like it's stiffer. So that second mechanical mode is going to be fundamentally stiffer and higher frequency. So we can scan faster, and we can also work in a regime where we don't have snap-in. So that's kind of a nice little place we kind of found through a lot of trial and error to really get good results. The fundamental mode, which now is going to be a bit softer than that second mechanical mode, will be the cantilever frequency at which we'll feel that force. So you can envision kind of firing the laser at a similar frequency and then pulling out that modulation that's now happening on the end of the tip. And so just as an example, this will be where our PiFM images come from, giving us the chemical signature of the sample. If we then look at that whole same concept in a little bit more detail, effectively what we're going to end up generating is when we modulate the laser light coming at the sample substrate and the tip, so that tip sample junction, we're going to end up generating this dipole-dipole attractive force. So that's what fundamentally is causing the cantilever to feel a force pulling towards the sample that we're going to then demodulate and basically equate to the absorption strength of the sample. And so you kind of think of it in the same way you do van der Waals forces, which are also a dipole-dipole interaction. As you get closer to the sample, you get kind of this attractive regime, and then you go into this repulsive regime. We'll be seeing a similar effect, but now on top of that van der Waals, we'll be having this sample absorption interaction with the light. Currently, a lot of our customer base already uses kind of the 770 to 1900 wave number regime. So depending on how versed you are in chemistry, this is the molecular fingerprint region. This is where you're going to get a lot of molecular information about the molecules. And then you'll be able to use various search engines, Know-it-all, or some of the Thermo Fisher's tools to kind of decode what those absorption spectra are. And you'll see a little bit more of that as we kind of go through the discussion here. Now, the cool thing is it's all bimodal. So we get to get this information at the same time. So as we're acquiring the PiFM image, we are acquiring topography, phase, your other traditional AFM channels at the same time. And so if you kind of flip over here to the far right column, you can kind of see now how we're looking at this polystyrene low density polyethylene blend and highlighting via absorption wave numbers for those two molecules, where the polystyrene molecules are or where the low density polyethylene molecules are. Now, I did want to highlight that this laser range has been kind of traditional for us, but we have just recently, over the last about year and a half, been now fully evaluating and are now selling a laser option that actually extends this from 550 to 7100 wave number. The real benefit there as you get to the lower wave numbers is you get to look at more oxides and heavier bonds. So it's a really nice addition to the instrument. So how does this agree with FTIR? I mean, why do we even want to use FTIR? Well, it's kind of the gold standard, right? We have this library of hundreds of thousands of different materials where there are known FTIR spectra for them. And now we can take PiFM and see, well, how does that correlate with these known types of materials? So here we just show four maybe commonly used ones just to kind of demonstrate that comparison. But we're looking at nylon, polyether sulfone, PES, PMMA, and polyimide. And you can really see from the colored lines, which are the PiFM spectra, in comparison to the dashed FTIR lines, that not only do you get the correct peak positions, but you also get the correct peak ratios. So this will help you start to understand nuances in your chemistry when you're seeing peak ratios that are a little different, or where the peaks are actually shifting because of different bond stresses that are changing from what might be your pristine material to some kind of either stressed material or some kind of composite hybrid material. So how does this, what is it we're really trying to do with this? I mean, the whole idea is we want higher resolution than what FTIR can give you because that spot is so large. And we're interested in looking at composites, nanocomposites, or just small structures. So if you give yourself this kind of cartoon, you can look at FTIR as being the red response here, which is this topographic image. Just imagine the whole ensemble there is what the FTIR is going to give you. Its resolution is not good enough to decode what's going on in this topographic image. But if you then look at the PiFM results in location 1, 2, and 3, which are highlighted by this blue, black, and yellow spot, you can see that we're pulling out individual components. And so you're seeing a change in kind of what peaks are represented. So if you look, let's say at the yellow spectrum here, you'll see there's a dominance in this 1100 region. Well, this is a silicon oxide bond region. If you then go to location 2 and 3, well, then you're seeing that silicon oxide is not as prevalent anymore, but you're seeing some carboxyl regions that are more prevalent and such. So what we do know about this particular sample that we're imaging here is that there is silica beads inside this composite, these little nodules, and that's what you're seeing in the yellow spectrum. But anyways, this kind of helps you visualize what we're trying to decode. And then the question you have to ask is, well, how sensitive can you guys be? What can you fundamentally do? Well, this is some recent work we've done in the last few months where we're down to effectively just about single molecule level sensitivity. Now, I'll put a caveat on that this is a very large molecule. So this is about a 3,000 molecular weight molecule. But the idea is that we can find locations where we're seeing those molecules and then actually park in those locations and take the PiFM spectra. So a little backstory on this sample is that it was originally given to us saying, okay, we have this monolayer, we want you guys to image it. And we go to image it and we don't see anything. But then once we start scanning at some known wave numbers for these peptoid molecules, which tend to be in the amide regions of about 1633, we suddenly go, wait a minute, there's little areas that are lighting up. So what was happening in the end is they were actually thought they were creating a monolayer, but washing off most of the molecules when they were processing. So at the end of the day, we were able to at least kind of identify our ability to sense at this level and also help them understand where in their processes they were having difficulties. So if we just spend a moment on the spectra here, you'll see a few different things. You'll see this rather large kind of green response, and that's sitting on a larger chunk of the material. You see it highlighted in the PiFM image at 1633. Then as the particles get smaller, you'll see the spectrum strength decreases. You see that with the red spectrum here. Some of the other peaks here that you're not seeing changes in is because those are not part of that molecule. Those are contaminants that are part of the sample process. There's a little bit of siloxanes that are known to be part of the process. And then there's also some plasticizers that are known to be part of the process. So we're actually picking up those residuals as well. So like I said, quite a sensitive approach. Now, if we start to just kind of look at some other applications and how you can start to deconstruct composites, here we're looking at these kind of traditional block copolymer fingerprint patterns. I imagine most people in the audience already know this, but just in case, I don't want to make any assumptions. Using block copolymers, using directed self-assembly, we can start to think of clever ways to do lithography through basically self-assembled molecules. And so that's what really the purpose of this kind of research is. By the end of the day, what we're looking for is we do see this ability to nicely highlight the carboxyl peaks for the PMMA. We're now also seeing the signature twin peaks we get for the polystyrene and a few others. This is kind of where they start. And then the purpose of this work was actually to do some hardening of some of the materials, particularly the PMMA. And so what they would do is they would actually take a similar sample and expose it to a kind of a vapor form of aluminum oxide. it'll infiltrate into the PMMA, and then we get the results that you're seeing on the right-hand side, where now we're seeing how the PS has changed in structure, how the PMMA has changed in structure, and now a signature for the aluminum oxide that is basically mixed in with the PMMA. Now that's hardened the PMMA, and so now when you pull off one or two of the materials, you're left with a harder mask. And then of course the topography, which was all obtained at the same time. Now if you look closely at kind of the PS image here, and you can see that we're getting into resolutions that are below 10 nanometers. In this particular case, we're seeing down to about 5 nanometer resolution of that material. And I think CD, that was done kind of like one of these 90-10 ratios on that edge to approximate that resolution. So what we find in comparison to the topography is that the PiFM imaging is actually more higher resolution. And this is partly just because of the antenna effect of the light, kind of how it focuses on the end of that tip, re-radiates, and it's tighter focused than the end of the probe itself. This is easily shown in electrostatic modeling. I threw in this slide because I know defects, failure analysis, things like this are always really important. One of the things we've been working on recently, while not directly associated with semiconductor research, but I think is relevant from an FA point of view, is looking at nanoplastics. And we here what we're seeing is just a composite of these plastics kind of mixed together, spin coated. And what we're identifying is where we're seeing nylon, where we're seeing polystyrene peaks, spheres, and where we're seeing PMMA. And so here's our topography, what you traditionally get from your AFM. Maybe you get some phase imaging with that, but now we can highlight where the polystyrene is, which is a 1493 wave number, and you can see this kind of cluster of particles up here lighting up. We could switch over to PMMA, which are these smaller ones, and you can see all the PMMA particles are lighting up, the nylon particles here, the PTFE, and then there was some gold material also mixed in. Now, gold doesn't have an IR signature, but it does have optical contrast. And so if we go to a non-resonant peak for the other materials, we can actually highlight kind of the index or refraction difference between the gold, or kind of the conductivity, really, if you will, because you can imagine the electric field from the light generating, this kind of standing wave inside those particles as well, giving signature there. So not so easy to say, oh, that's definitely gold, but we happen to know it was already there, and so we were able to highlight that. And then just kind of shows, a clever way to kind of overlay what was what in that mixture. I think what is really important to understand with PiFM compared to other Nano-IR techniques or scattering SNOM techniques is that we are able to identify both organic and inorganic materials without any kind of tricks. The fundamental microscopy technique that we use, PiFM, is sensitive to both. Scattering SNOM will kind of head towards more the inorganics, and the kind of photothermal techniques will hedge more towards the organics, but not be able to do both equally well. So now we put ourselves into the mix here, and the idea is that we're bringing in molecular information, mapping. I don't have slides here, but we can do like hyperspectral imaging, things like this with a 5 nanometer resolution, 20 nanometer surface sensitivity from monolayers to 20 nanometers thick. And we also have another modality where we can look at bulk samples as well. Okay, so let's get in a little bit into the semiconductor side of things. So where we started with is we were collaborating with a group here in the San Jose area at the IBM Almaden Research Lab. And what we were looking for is signatures of latent EUV images. What we found is that there are small chemical shifts that you get in certain bonds, and also relative strength changes when basically the resistance has been exposed. And so we did see, a drop in the carboxyl peak region. We do see, if we kind of zoom in to this 1500, 1400 region, we get a peak shift, we get a peak doubling. We can use this information about as it's being exposed and how the chemistry is changing to help us understand how that's working. So let's just show from a topographic standpoint what you would see. Well, you get shrinkage of those materials, so we definitely will see some of that in the topography. But what PiFM is able to show you is exactly how it was really exposed. Here you can kind of see, well, I see some Fs. They're kind of rounded on the edges, but actually the image that was formed, the PiFM can show you that at this 1274 wave number that we chose, really kind of definitively, but no, that's not what the shape looked like, in terms of the projection. That's just what we've been seeing in topography. And of course, the phase channel is not able to give us any of that kind of information. So if we go and start looking at some other examples of this, here we're looking at different dosages that were used to expose the resist. And really from the topographic side of things, there's a little bit of roughness difference between the three images, but how are you going to make a lot of correlation there? If we start to again look at the PiFM at the 1280, we can see as the dosage level increased, a stronger contrast in those pits that were exposed. And then again, trying to give us more information on what's happening there beyond just the topographic lay of the land. Same kind of experiment kind of done here. This is with some colleagues at TNO in the Netherlands that have been working with us. And you can see again, we have the topography where there's kind of exposed lines. Same thing in the IR PiFM, but you can see how nicely resolved those lines are. So we really get a clear picture of how well they were aligned. And it actually correlated quite well with the kind of CDM kind of technologies to also look at how well those were defined. And so just the traditional scan probe couldn't tell you this just from topography on how well it was defined, but the IR could. Other kind of defect analysis that we've looked at, this is one where effectively you had a substrate of, there are kind of two different coatings on top of a silicon substrate. And at the end of the day, the real problem they were seeing was just they had a lot of particles and a lot of kind of debris on these substrates. They want to know what that was coming from. In the dark field, you do see a lot of these little spots here and there. You see maybe a little bit of smearing on the bottom. So it's not quite easily clear. So what we did here is we went in and imaged. Okay, thank you. Looked at the topography. And then just to kind of make topography easier to see, we then just kind of changed the scaling there so that you could easily see texture. And again, here what we're doing is looking at each one of these particles that we're seeing, taking spectra on those particles. So to take those spectra, we're just tuning the laser and absorbing and looking at the absorption response. And what we find is that sometimes you'll have a very strong response. And what you'll want to do is intentionally lower the laser power at different regions within the spectrum, just so that you don't overwhelm the your ability to see the smaller peaks by having some really large peak in there. And so that's what's going on here. The boxed region used a much lower power percentage, and the unboxed region a higher power percentage. Right. So you can see we have a couple things going on here. And we're seeing kind of a similar spectrum throughout the sample. So what our conclusion was there was that effectively this material even got a coating across it, and then there's some chunks of it here and there that give maybe a slightly larger signal. So here we renormalized the power so that all the peaks are of equal ratio, right? So in our previous slide, we're taking the two power regions differently. Now we're going to normalize those two as you would just expect from a normal FTIR machine. And you can see we do have a collection of peaks in this 1400 region and a collection of peaks in this kind of 1000 region. And so if we take those spectra and we run it in Know-it-all, then what we can find is that it thinks the primary peak is silicon. So yeah, I mean, it's on a silicon substrate. So definitely, we definitely would have expected that. The next one that we got is one where we had to effectively tell Know-it-all to ignore that peak and look at the other peaks. And then we were able to match that with this kind of B5Y acid. And that we've then determined was the contamination. Now, we've done this quite a bit on mini samples. We even offer kind of contract service work where we do this quite a bit. And it's quite insightful on when you can take the spectra and run them in the library and start doing your forensics and decoding what's really kind of going on. So, that was kind of a pretty specialized thing, but another thing that we've done quite a bit recently is just, looking at defects. The way this would typically work, and during the discussions, we can definitely correct me if I'm misguided in this comment, but, you take a topographic image, you see this shaped defect, and then you would say, okay, well, that shape kind of infers it's maybe something like this. And then you have this catalog of all these images where, okay, I think it's this because the shape matches, And, but from our perspective, we don't need to know that. We can simply, on this Teflon particle, take the purple spectrum, which just shows us some substrate, the silicon oxide, and then with silicon, the native oxide, and then go on to the particle itself, take the blue spectrum and get a very nice FTIR spectrum for Teflon. Did the same here for polypropylene on off. You see no peaks for 1 and 2, just substrate, which is off the particle. And then once you're on the particle, you see the signature for polypropylene. An interesting thing about the one up here in the upper right-hand corner is off the particle and on the particle, you get similar spectra, but they're different enough. And where the difference is coming from is that you are seeing the silicon substrate, but on the particle, you're also seeing silicon, but it's not the same. One is the polishing silica that you would use, and then the other one was from the substrate itself. And so you are getting 2 different spectra from that. And we do get a clue in this 1260 peak here about crystallinity, and that's kind of helping us make that judgment. Okay, to kind of wrap that up, first off, yeah, it is certainly quite early in the morning here, but it's our pleasure at Molecular Vista to give the talk, and mine as well. I do want to give a special thanks to everybody who's organizing the symposium. I know that's a lot of work. I've done these on my own as well. Justina, thank you so much for organizing all the online components and working with us to get this going. I am going to try to stick around for the panel session coming up after the next talk, so I can answer questions there as well, and here as well. But if you have anything specific you want to talk to us about that's big encompassing, info at Molecular Vista is a great way to get a hold of the team, and you can check out our website as well. And we're always very happy to coordinate sample evaluations or even do contract service work if those things are interesting to you.
All right, thank you very much. So we have time for maybe a quick question before we go to the next talk. Does anyone have a question? Yes, Gernot.
If you're looking at the distribution of chemical maps, do you use peak height or peak area for showing the distribution map?
So I'm sorry, just to ask that one more time. It was a little muffled, but
basically, if you look at the distribution of chemical substances, you sit on a certain band, and to show the distribution, you could either use peak height at a certain position or use peak area. Which one would you use?
Peak height or peak area? I mean, are you talking about from just looking at the spectra themselves or the AFM images?
If you look at the chemical distribution of a certain substance, let's say you want to see the PMMA distribution over X of whatever.
Oh, I see. So you're kind of referring to something like this spectrum here.
One side, red picture PMMA distribution. Is that quite a big area?
Yeah, I'm actually, I apologize. I don't know if I'm fully following the question. I mean, of course, we could, if we're interested in how much area coverage, let's say, one chemical has versus the other, we could post-process that and determine area.
Okay, that's the writer.
Yeah. Okay.